Hello, I welcome you all for next type of experimental design. In this video, we'll be learning on another type, that is Latin square design, LSD. Now, this is a type of RCBD, that is randomized control block design only, but it has got a special feature here. In this particular design of experiment, we try to reduce the number of experiment. The sample required will be reduced. Now what we do here is, in this particular experiment, each experiment we consider it as one block. Each experiment is considered as one block, and the primary factor, minimum number of factor here is 3. You cannot have 2 factor for LSD, minimum is 3. It's a special type design, that's what I have told you earlier. And another special feature is the level of each factor should be equal. That means level for factor 1, factor 2, factor 3. Factor 1, that is x1, is nuisance factor, x2 is again a nuisance factor, x3 is the primary factor. For all three factors, that is k is equal to 3 means factors, 3 factors, the levels L1, L2 and L3 are equal. It could be 2 level, or it could be 3 level, or 4 level, or 5 level, whatever may be the levels, it should be equal in size. So the sample size will be equal to n is equal to the number of samples will be equal to L square. L square. So that is why the name Latin square, squared design. Now just to compare it, if you perform the experiment with the RCBD, same number of factors, 3 factor, and 3 levels. For each factor, if you take 3 levels, in RCBT it would have been 3 into 3 into 3, 27 experiment would have been done. 3 levels, 3 factor, 27 experiment would have done. Now in this case, Latin square design, the number of experiment will be 3 square, so that is 9. 9 experiment would have to be done. So the sample size decreases when you take Latin square design compared to RCBD. So RCBD is the larger version where you work with the higher number of sample, whereas in Latin square design you work with the less number of sample. So that is the advantage of using Latin square design. Now there are higher versions of it. You can use 4 factors. So for 3 factor it is specifically named as Latin square. If you take 4 factors, that means 3 nuisance factor, x1, x2, x3 nuisance factor, and 1 primary factor. If you take that, it's called as Greco-Latin square. Similarly, if you take 5 factor, it is called as Hyper-Greco-Latin square. More than that, it becomes complicated. So maximum 3 level, 3 factor, 4 factor, 5 factor can be used under Latin square design. Preferably more than 5 is not good in terms of analysis. Now to identify, the factors are identified as x1, x2, x3. To identify the levels, each factor is given with one terminology. Maybe first two nuisance factor. For example, here we have taken one case. Let's analyze with this particular case. K is equal to 3. That is 3 factors are there. x1, x2, x3. Each has got 3 level. So L is equal to 3. So obviously 3 power 3 square, n is equal to 9. That 9 experiment you will have to perform. Now these 9 experiment, each factor is given with one terminology. That is, first nuisance factor is given as 1, 2, 3. 3 levels, level 1, level 2, level 3. Second nuisance factor x2, given again 1, 2, 3. Now when you go for next level x3, x4, x5 in further, you will have to give unique characters. Maybe you can give ABC, you can also give alpha, beta, gamma, or you can also give some other nomenclature like M, M and P kind of thing. Now when you synchronize or convert it to a tabular format, you can perform in this format. That is x1 in the column, x2 in the horizontal row, and inside the box x3. Further x4, x5, x5 you can attach it, and you can see that there is only one letter written inside, A, B, C, CAB, BCA. How will we get it? This is the experiment number 1, that is 1, 1, K. First row, first row, first column, and the experiment set is inside this EA. So for this particular combination, that is 1 1 EA, this combination will perform the experiment. Remember, 1 means a particular level. If you take the case of age, that will be uh, children, adult, old age, that kind of levels you can have. Or if you want to see the temperature, maybe some 20 degree, 30 degree, 40 degree, that kind of numerically they will have certain values. So you perform this experiment at level 1 1 and A. Similarly, second one, that is first row, second column, first row, second column, and the variable x is B. So this is the combination. Likewise, you will have 9 combination. So 1 1 A, 1 2 B. Similarly, at the end 3 3 A. Let this one, third row, third column A. Now, first two always it is given as 1 2, first two instance factors, that is row wise and column wise. So that is why we do, just in order to avoid the um, uh, clumsiness over there, just in order to avoid too much of characters, they are given like that 1 1 kind of thing, 1 2 3 1 2 3. Continue, can continue up to 4 5 like that, based on the required levels. Now the advantage here is you can see only one letter. It means if you see one letter, that means there are three factors. Always the numbers that is written inside the box is k minus 2. K means number of factors. You have three factors, you can see only one letter here. That means 3 minus 2. One is given for rows and another one is given for column. So those two are not written in the box. So A is written, this means it means 1 1 A. So it is automatically understood that it is first row, first column. This is the order in which you perform the experiment. Now let's take another example. Take a quick look at this box 1, this is box 2. You can pause the video for certain amount of time. Just try to understand this table and this table. What I want you to do is you find out how many factors are there, how many levels are there for each, for this as well as this. Remember, these two are separate combinations. Now at this point, pause the video and come back again. Alright, welcome you back. Now let us see the answer. You might have thought about this particular combination. First let us look at this. I have told you already, it is k minus 2. So if you see two characters here, A and alpha, that means it must be for two different factors. So another one factor is row, another one factor is columns. So nuisance factor 1, nuisance factor 2, x1 in the rows, x2 in the columns. So two more are there. Third nuisance factor is A. Your actual variable, design variable is alpha. So how many factors are there? One for the row, one for the column, one for this EA, another for this. Totally 4 factors are there, right? Alright, 4 factors are there. Now L is equal to 5. That is 5 levels we have used. How did I get to know that L is equal to 5? There are two easy ways. One, you can see this A, B, C, D, E. So 5 levels are there for factor 3, x3. Alpha, beta, gamma, delta, epsilon. Again, that's also 5. That is for the x4, factor number 4. And otherwise also, the number of exponent is 25. L square is equal to 25. So each should have the equal level. 5 rows, 5 columns. This 1, 2, 3, 4, 5, 4. Factor x1 and x2. Factor number x3, it is A, B, C, D, E. Factor number 4, alpha, beta, gamma, delta. So similarly, in this case, you have 5 factors here. 4 levels are there. So there are 3 values, A alpha 1, one for the row, one for the column. So totally 5 values you have to consider, 5 factors, and there are 16 experiments. So each has 4 levels, 16. Right? Next, the model equation that you will be taking here is similar to your previous experiment, that is RCBD. Now let me look into this, that is mu, mean. There may be a natural variation, that's why each values may not be same. So let me consider natural variation, mu and alpha, but still the individual values are different. There is a possibility that your main factor, that is last one alpha beta what we have taken, that is our treatment factor, design factor, that may be affecting, or it may be affecting because of the row, or it may be affecting because of the column. So for each number of factor you will get one term. So in this case three factors are there, x3, x2, x1. So three different factors we have. So whether they are significant or not, whether the effect caused by this are significant or not, you can identify using one ANOVA table. ANOVA table goes in a similar way for the treatment, that is our main factor, design factor or a primary factor. These are all nuisance factor, nuisance factor 1, nuisance factor 2. You can include many more. For each factor you will weigh it or compare it with respect to natural variation, that is error. So F test is used throughout. So the treatment MST, treatment versus MSC, treatment versus MSC, treatment versus MSC. We'll compare it. We'll have a F test. We'll get to know whether the treatment is significant or other nuisance factors are also significant. So ideally nuisance factors we assume that they are insignificant, but we will come to know here whether they are significant or not. The most important feature you have to see here is degrees of freedom for all the factors, irrespective of the type, primary or nuisance. Their degrees of freedom is same. The reason is the treatment has T number of level, T level we have. Similarly, for other factors also it is same. The levels are same. Since the levels are same, their degrees of freedom is also same. That is level minus 1. And the total number of degrees of freedom, total degrees of freedom will be t square minus 1, the number of experiment minus 1. In earlier case we had 5 level, 25 experiments were there. For 5 level, 25 experiments were there, so 24 would be the degrees of freedom. Here it is individually we will have to take level minus 1, and it is same for all factors. The remaining degrees of freedom, total minus this summation, will be the degrees of freedom for the error. Rest it is similar to the ANOVA experiment, we have to perform it. That is what you can learn over here. So summarizing, we have seen what is Latin square design, how the number of sample size, and we have seen that the sample size is lesser compared to the RCBD. Always the last factor with the primary factor, you can have three nuisance factor, two nuisance factor, three nuisance factor, or three nuisance factor maximum. All the levels will be same in for all the factors, and we assign it in the box like this, and it's always a square design. The experiments are always square. So we have seen the model equation as well as ANOVA. That's the end of this particular video lecture. Thank you.